Year 12 students, I can't believe we're back here in lockdown again. I thought that was last year, but who knows? We could be back on Friday. We might be here for a little bit longer. I guess we'll just wait and see. Wait and see. A little bit more cases today. I'm recording this on Monday than have been the last couple of days, and unfortunately, with this pandemic that's going on and the virus itself. It's a little bit unpredictable because of the gestational period of the virus, and so how long it can stay on a surface, and if somebody touches that and then touches their eye or their nose or their mouth with their hand, then they have become infected, but they are asymptomatic for a short period of time. So you feel fine, you feel no problems, you're still out and going to work and going to shops, etc., and all of a sudden you've infected another 3 or 4 people. So it's just this sort of waiting game, and I guess I understand where the government's coming from when they make those decisions, but for us here at school, we're just going to play it by ear and go day by day. Last year we were ready to roll SACs and mid-year exams and stuff like that out online for all year levels. So for us, we're ready to go if that's what's required. Hopefully we're talking week 9. I believe it's the Thursday of week 9 is our SAC for PE, and hopefully that we're back in person long before then. But look, we've got fingers crossed and we're just waiting to see. It's day by day at the moment. So today's lesson, I wanted to go through with everybody the fatigue and recovery stuff. So basically the lesson that we've had on fatigue and recovery so far, I went in a very, very basic nature about most of the fatiguing mechanisms within the human body and a very basic representation of how we recover each of those mechanisms. So I think that what's really important now is that we think about getting into a bit more depth. So I'm going to flick through this relatively quickly but stop on a few points. Feel free to pause the video, make some notes along the way, but also write down any questions you have as we go, things that didn't make sense to you, things that you want clarified, etc. for when we join back up in the Zoom meeting later on in this lesson. So, energy systems, fatigue and recovery mechanisms, okay? And as we said, fatigue of a muscle is defined by its inability to contract to the force that we're desiring it to. So if I am trying to jump further, if I'm trying to run faster, if I am trying to lift a weight, for example, and the muscle will not contract to the force where I want it to contract to, but it once was, I am fatigued in that muscle. Okay, and while there are many reasons why we fatigue, one will be more significant to the others, and that is the main cause of fatigue. So we had a look and we spent a bit of time at the main factors that contribute to fatigue, and we went through, you can deplete your fuel stores, so you start running out of the stuff that gives you energy, or you start building up accumulation of the negative things. And we looked in detail about what hydrogen ions do to the acidity levels of pH within the muscle, and we also looked at inorganic phosphates and what they do in terms of the tropomyosin and what they do in terms of the inability for the muscle to contract as many contraction sites of actin and myosin, so we deplete our muscular power that we can generate there. So then we were looking at things like elevated body temperature. So what happens when we get a high body temperature? The body wanting to stay within that homeostasis. We sweat, we decrease our plasma levels, the viscosity of our blood becomes thicker and therefore it's harder to pump around, therefore it elevates the blood pressure. And finally, the brain itself decreases the firing of the central nervous system. So that means the messages being sent to the muscles will start to slow down. Now, all 3 energy systems work together to rebuild ATP or resynthesize it. And because all 3 energy systems work together, then we have a drop in the fuel sources within each of the 3 energy systems. So if phosphate creatine is the fuel for ATP resynthesis, then phosphate creatine is the fuel that can deplete. Glucose is the fuel for anaerobic glycolysis, and glucose is also the fuel for aerobic glycolysis. And then we have fats, which is our aerobic lipolysis. And so when we deplete phosphate creatine, Energy has to come from anaerobic glycolysis. It's the next fastest energy system. It is a slower rate than the phosphate creatine system. So firstly, we slow down because the ability to resynthesize ATP happens slower. That's one of the reasons that we slow down when we run out of phosphate creatine. But also the fact that phosphate creatine is a one-step reaction where the phosphate and creatine release their bond, and that energy resynthesize ATP. It's such a basic manipulation of energy moving. So when we actually deplete phosphate creatine, we want a passive recovery. Remember, a passive recovery is doing nothing. So a passive recovery is when we literally lie down, stand still, sit still. And that gives our body the opportunity to replenish phosphate creatine. So we might be able to use that as a predominant energy source once again a bit later on in exercise. So 70% of phosphate creatine within 30 seconds of passive rest, up to 90% within 90 seconds, and then all the way up to 100% at about 3 to 5 minutes. I have seen statistics that push this out to 98% in 3 minutes, and it can take up to 27 to 30 minutes to get full 100% phosphate creatine stores, but for our course, these are the numbers that we stick with most generally. All right, so carbs, fats, and proteins. The rate of ATP production from aerobic use is about 50 to 100% faster than the rate of aerobic use of fats. So if we have to run out of carbohydrates and glucose and flip over to fats, we've mentioned that is called hitting the wall. And it's not the crossover effect. The crossover effect is when we have been efficiently burning fats and then we have to turn to glucose as our main fuel source. So that's a different one, the crossover effect, but this one's the opposite way around. We are burning carbohydrates because they're a faster fuel. They're 50 to 100% faster to burn than fats. But if we start to run out of glycogen, we lead to fatigue because we have to use fats then, and fats take 50 to 100% longer to actually break down in comparison to the glucose that we were using. And then proteins, which is those extreme circumstances, they take even longer than fats and carbohydrates, and they have a huge amount of oxygen cost to be able to complete that reaction. So if we want to resynthesize, refuel our glycogen stores, we want high GI foods, and we want them as soon as possible after the event has taken place. Now, one thing that's really interesting here is that the insulin that occurs. Now, when we consume glucose in our body, insulin is created through the pancreas. And insulin and glucose work together to help the body absorb different bits and pieces and processes take place. Now, when we have insulin responses, our insulin is already responding well within the first 30 to 45 minutes after exercise. So if you want the glycogen stores to replenish quicker, if you want your glucose levels to be back to where they were at resting levels, then you want to be consuming the carbohydrates within 30 to 40 minutes of the end of exercise. So what that's saying is that as I go out to my garage and I complete my workout and I go on the treadmill and I'm running, and my body has been burning through glucose and glycogen, insulin has been being produced and pumped through my body. So what I want to do is I want to make the most of the fact that there are excess levels of insulin within my body. And as soon as I finish that workout, I want to come inside and I want to have something that's high GI, really quick to break down carbohydrate, because with the extra insulin already in my body, that's one less process that I have to wait for my body to go through in order to store some of those carbohydrates as glycogen and transport as glucose throughout my body. So I'll return to resting levels quicker if I'm able to do that. So if it's within 1 hour, preferably between that 30 to 45 minutes, then 55% of glycogen in the next 5 hours and 100% restoration rate within 24 hours. If it is 1 to 2 hours after exercise, then it can take 24 to 48 hours, up to 2 days, to get 100% store. If you don't consume the glycogen until 5 hours after exercise has finished, it can actually take up to 5 days to fully restore those levels in the body. Now, we talked about accumulation of metabolic byproducts. So we actually start to build up the inorganic phosphates and the hydrogen ions. I don't need to revisit those. We went through them in detail the other day in class, and I think everyone should be comfortable on that so far about what the hydrogen ions and the inorganic phosphates do within our body. Lactic acid is always in the body. It never goes down to zero, but lactic acid, including those hydrogen ions, will start to really peak their levels once we exceed the lactate inflection point. And the lactate inflection point is when the lactate production exceeds the removal. So we start to exponentially increase the amount of stores that we have of that. Now, we've mentioned lactate inflection point a fair bit. We have never mentioned the maximum lactate steady state, but we have mentioned the fact that we are able to remain at a steady state when working at the lip or lactate threshold. So the maximum intensity of which our lactate stays at a steady state makes sense that that is our lactate inflection point. And if we work above that, this exponential increase means that at that 12.2 kilometers per hour or whatever it might be, we will not be able to sustain that intensity. Our muscles will go through muscle acidosis and our body will actually start shutting down muscular contractions because of its need to stay in homeostasis, regular conditions. Okay. Lactate inflection point is around about 85% of the max heart rate for most people, but some people are able to push it higher, up to that 95% of your max heart rate for elite athletes. Hydrogen ions, again, we've talked about what the hydrogen ions does. Reduced rate of glycolysis, well, that's because there's actually less muscular sites that are asking for stores of fuel. Inhibited excitation and contracting coupling, well, that makes sense because of the tropomyosin line moving. We talked about that. And then reduced cross-bridge cycling, which means that there's less areas for that actin and myosin to cross-bridge onto each other, which makes sense. So how do we remove hydrogen ions? Hydrogen ions need to be taken into the bloodstream, okay? They need to be removed, but we also need to make sure that we are getting oxygen into our muscles, okay? So what we can actually do here is an active recovery. We can keep our oxygen levels high, which also is going to require us doing a cool down or exercising. Active recovery means exercising the same way at a lower intensity. So if we're able to do that, then we create this muscle pump where our muscles are continually working and they are pushing the blood up through the valves. The valves close and therefore we are continuing to flow blood through the body. We're trying to cycle through the hydrogen ions, the oxygen, and the blood lactate to move everything out and not let it venous pull, which means stay where it is. That's also going to cause issues with muscle tears and muscle damages in the short-term future. Okay, so active recovery is critical for hydrogen ion removal. Now, rehydration. If we are completing exercise where we are going to be creating a lot of heat in our body, therefore aerobic respiration, what we're actually going to be doing is creating a lot of heat and therefore we're going to be sweating. When we sweat, we are losing plasma and volume of liquid inside our blood and we are actually dehydrating. Now, rehydration can include hydration, which is water, but it can also be hydrating our carbohydrate stores, which means that we are going to be consuming things like Gatorade, Powerade, etc. In the liquid form, not only are we hydrating our bodies, but we're also replacing electrolytes, and electrolytes' job is to help, similar to enzymes, processes happen inside the body. So electrolytes are really critical for muscular contractions, for removal of lactate, for the mitochondria and myoglobin to be working with oxygen. We need electrolytes in our body. Now, electrolytes sit within that liquid and plasma. And so if we are sweating out a lot of our plasma levels inside the body, we're actually sweating out those electrolytes, which means that a lot of those jobs inside the human body, a lot of the functions are unable to take place as efficiently because we're losing electrolyte levels. So what we need to really think about when we're choosing a sports drink or a water is, are we actually sweating out and losing electrolytes, just fluid, Or are we burning through a lot of glucose and glycogen? So that's actually three different things that we can actually replace here. We can replace the carbohydrates through our sports drinks. We can replace electrolytes, which are the salts, okay? And we can replace the plasma levels, which is simply just the water. So there's three different types, and we'll talk about them more in detail later on. There's actually some other stuff that's going on at the moment in terms of investigations and looking about different things that are taking place inside the human body to do with potassium, sodium, calcium, etc. But we don't need to go through them in terms of our course. I just want to let you know that they are currently taking place in terms of studies, okay? Lactic acid, all right? So we need to remember that lactate is actually something that can be reused. So if we are able to move the lactate into the liver, we are able to get glucose and glycogen for further contractions of muscles using glycolysis in the future. However, the hydrogen ions is the stuff that is acidic and that creates the acidosis in the muscle, which decreases the pH, okay? So we need to remember that lactic acid, being used as a term, covers both lactate and hydrogen ions. And if you are posed with a question about fatigue and recovery, you need to be very careful that you are using the right word, either lactate or hydrogen ions or lactic acid, depending on what you're talking about. So showing the examiner that you have an understanding of the separation between the two and the fact that lactate can have a positive that's attached to it as well, but the hydrogen ion is that acidic negative. You need to really think about how you're wording those style of answers to your questions, okay? Okay, we continue on. Muscle buffering, all right, so this is where we talk about our ability to try and neutralize the acid and the pH change. One of the things I wanted to bring to your attention here is about sodium bicarbonate. So, what we've talked about a lot in class is the fact that we have a pH scale. And on that pH scale that goes from 1 to 14, we sit roughly around that 7 mark. And we were talking the other day about 7.35, etc. We know that if we start to get too much acid in our body, that goes down towards that number 7, 6, 5, etc. And what we actually know is that you can balance this out by moving it back the other way with what we call a base or an alkali. Okay, so when the body has too much acid, it produces a base which tries to buffer out and bring that pH needle back to the middle where it wants to sit in between that 1 to 14 of the pH scale. What a lot of athletes found is that sodium bicarbonate, the same sort of stuff that you can buy at the shop, bicarbonate soda, is actually a very powerful base or alkali. And so athletes who knew that they were going to be performing exercise that was going to be using a fair bit of anaerobic glycolysis dominance would actually start consuming sodium bicarbonate just in water as a drink pre-exercise. So what they were doing was they were actually loading their body up with an alkali level pH, so above that comfortable level of 7.35. And then as the athlete was going to continue exercising and producing hydrogen ions, it's actually bringing the pH scale back to where it wants to be. So it's this pre-buffering idea that a lot of athletes were doing at the start of exercise or pre-exercise. You need to be really careful because some aspects of anti-doping have actually seen the use of bicarbonate as illegal, and so you just need to be careful about this. And also, over-consuming is going to tip the pH scale in the wrong direction. So if you are thinking about this, make sure you do a fair bit of research into how much to consume, and also be really careful about this sort of stuff and whether the body is actually going to benefit from bringing an alkali into the system beforehand. But it is interesting to know that it's something that we're able to do. The word is buffering, and the buffering refers to moving hydrogen ions and being able to keep the pH in its balanced scale. Okay. Now, we've talked a fair bit about lactate inflection point, okay? We've talked about the exercise intensities. We've talked about all this sort of stuff. So if I'm looking at these three athletes here, and I'm seeing this athlete's lactate levels in their blood are spiking. That says to me that they are working at an intensity above their lactate inflection point. These two athletes that are able to keep their blood lactate levels down, they are actually going to be able to complete the race in a faster time, because what they're going to do is they're going to be able to keep their muscles from experiencing acidosis until a later point. You need to be really careful when you read these graphs that you ensure that you actually are reading the axes properly, because sometimes it'll be intensity down here, sometimes it will be time or duration. So you can see in this graph, we've got to look at the 11 kilometers per hour, 12 kilometers per hour, and 13 kilometers per hour. And so each of these athletes was completing 15 minutes and then another 15 minutes and another 15 minutes in 3 different speeds. All 3 athletes for the first 15 minutes at 11 kilometers per hour were able to work under their lactate inflection point. Working at 12 kilometers per hour, this athlete here, athlete number 2, was obviously working above their lactate inflection point because they started spiking. Whereas athletes 1 and 3 stayed steady state throughout that 12 kilometer per hour intensity. As they moved to the 13 kilometer per hour intensity, you'll notice that athlete 1 had a real spike, but was able to balance it out at the end, whereas athlete 3 was actually remaining relatively stable at 13 kilometers per hour. So my guess is that athlete 2 had a lowest lactate inflection point. Athlete 1 had the next lactate inflection point at around about the 13 kilometer per hour, and we still haven't seen what athlete 3's lactate inflection point is because they're still able to remain relatively stable at that intensity. So you've got to make sure that you really are taking the time to read these graphs properly. Okay. All right, so muscles and their excitability. Now, the impairment process of electrical impulses, so motor neuron, the message that's being sent, okay, a lot of these things, hydrogen ion, inorganic phosphates, ADP, and potentially potassium, can actually affect the contractile, all right? But what we need to think about is the central fatigue mechanisms. So, the central nervous system, okay, when the nerve is actually there and the messages are being sent over to the muscle, it's actually this jumping point from the end of the nerve to the muscle that sends the message to say, hey, you can contract now, okay? If this neuromuscular junction, the point where it jumps, is actually fatiguing, there is actually a reduction in the release of the stuff that allows for these messages to be transmitted across that. So what's going to happen is the brain is still going to be sending the messages down, but the muscle is refusing to accept that message. That is the central nervous system fatigue that's taking place in that point, okay? So it's actually going to be sending a message back to the brain saying, hey, I did not receive your message, or if I did, I've chosen not to accept it. My muscle is not contracting, so the brain ends up sending less messages down to the muscle, all right? Now, peripheral means the external parts of the body, all right? And some of the fatigue mechanisms at the external parts of the body are talking about blood flow and body temperature. I know that we've mentioned about this a fair bit, but I wanted to cover it one more time. The body will have a huge demand for oxygen, okay? The body has got a large amount of waste products as well, the lactate, the hydrogen ions. Because of this, not only is my body trying to deliver a huge amount of oxygen to the working muscles to work aerobically at higher intensities. But what's also going to happen is my muscles are now asking for more oxygen and more blood flow to be able to remove some of the lactic acid, the lactate, get it into the bloodstream, move it to the liver, and the hydrogen ions try and oxidize some of those hydrogen ions so that it can buffer out that pH level at the same time, which is therefore going to be putting more stress on my body to try and work harder. Now, the body has to make a choice. That oxygen that I'm sending down to the muscle, do I send it there to try and buffer out some of those hydrogen ions and flush out some of the lactate? If that's the case, then the energy that I'm going to have to be using for the new bits of ATP resynthesis have to be anaerobic. Or do I stay in the aerobic energy system with this huge amount of oxygen that I've managed to get into my muscle? However, I'm still suffering from acidosis where my pH level is at a level where I'm not staying in homeostasis, which is regular functioning of the human body. So the body's got a really hard choice to make. So we end up with a huge amount of blood volume going to the working muscles. Our cardiac output increases majorly, and the vital organs, things like the brain, the heart itself, the lungs, they actually get less blood flow. The skin can also get less blood flow because the muscles are demanding it. And if the skin starts to get less blood flow, then we're not actually able to sweat out as much as we were. So we stop this whole thermoregulation business, which was keeping us, again, within homeostasis, the body's correct temperature. Now, if the blood is not being brought to the surface and it's not sweating out, that's an issue because the body is going to overheat, which means that the brain will tell the body to shut off as a protective mechanism. Okay, so you need to understand how all of these things are interrelated with each other. Now, here's a really interesting one. This is what the blood flow is looking at for the skeletal muscles, the working muscles. And here's where all the other organs in the body, you can think about things like kidney, liver, stomach, brain, are actually receiving enough blood and therefore oxygen. So it starts off with 80% of the organs in the body are receiving blood flow and only 20% of my muscles are. But within 4 minutes of maximal exercise, I'm actually at 80% of my body is getting my blood flow, my muscles are getting my blood flow, and only 20% of my organs are getting blood flow. So that's really dangerous for the brain to be getting that lack of oxygen for 4 minutes trying to work at maximal intensity. And that explains another reason why we can't sustain maximal intensity for that long. Now, dehydration means a lack of fluid and water within our body. The body consists of up to 80% water. A lot of that is in our blood and in our brain. Okay, it helps our organs, and our muscles are made up of a lot of water. So dehydration means that all of these things are going to stop working properly. If we lose a lot of sweat, we can lose the salts and electrolytes. We lose our coordination, our decision-making abilities. Our cardiovascular system doesn't work effectively. We have a huge rise in our body temperature, which means, again, we're going to have to sweat more out to cool ourselves down. So the duration and intensity of exercise can really affect dehydration. So the longer an event is, the longer I'm sweating for, the less fluids I have in my body. The higher the intensity, the quicker that I'm going to have to sweat because I call upon aerobic energy at higher levels. So therefore, the byproducts that I'm creating, including that heat, is happening at a higher level. You can slow dehydration down by intaking fluids during exercise or before exercise, ensuring that you have a large amount of fluids inside your body already. Athletes can make sure that they trying to tolerate drinking by training themselves. A lot of us find it really difficult to consume fluids during exercise. It's a taste thing. It's a mindfulness thing. And what's really important is to know what can that do to your body if you do not do this. Now, if dehydrated, cramps will ensue. Now, we don't know a huge amount about cramps and stitches in the human body and why they take place, but one thing we do know is that dehydration will lead to more cramping of the muscles. Heat stress and heat stroke, meaning that the body is overcome by a huge amount of heat, poor performance, and increased risk of injury when things are not hydrated. So, when you start to get dehydrated, you will have severe thirst. You'll have a dry mouth or dry lips. Your urine amount will decrease and the urine will become darker. Your breathing rate will be higher, trying to bring some oxygen in from external so it can potentially form more H2O inside the body. Lightheadedness because of the blood flow not going to the brain anymore, and nausea, that feeling of headache or sickness. You could actually get confusion because of that lack of blood to the brain again. So what's really important here is that we understand that when we are starting to dehydrate, it's not only the fluid that we're losing, it's potentially the electrolytes that we're losing as well. And there's a couple of little facts over here about 2%. So somebody who's 50 kilos and might lose 1 kilogram of fluid, their performance can go down by 10 to 20%. So that's a huge amount of decreased drop by just losing 1 kilogram or 1 liter of sweat, which for some people who sweat a lot, that can happen pretty quickly. Okay, so knowing that sweat is really important for us, we need to make sure that we reduce the potential risks of dehydration. So if you are starting to suffer from any of those things that I mentioned earlier about the dry mouth, etc., that means you are already dehydrated. So what we need to look at here is we need to look at the fact that we want to avoid it before it happens. So drink water. If you are doing exercise that's 1 hour plus, then use sports drinks. Okay, before the 1 hour plus, you don't need to be replenishing that much glucose and glycogen if you've been eating properly beforehand. Okay, avoid starting exercise if you're already dehydrated. So drink water pre-exercise. So they're saying here half a litre, 500 mils within half an hour to 60 minutes prior to your game taking place. And then drink 200 mils of water every 15 minutes. A lot of people will weigh themselves before and after sport. 1 kilogram is 1 litre. So if you weighed 81 kilograms pre-game and after the game it's 80 kilograms, then you know that you've lost 1 litre. Quite often they talk about the 1.5 rule. And so once you know how much weight you've lost, you multiply that by 1.5. So if I did weigh 81 kilos, I went for a long run, I was sweating a lot, I came back, I weighed myself on the scales, I'm down to 80 kilos. That means I've lost 1 litre of fluid. I would need to replenish 1.5 times that. So that's 1.5 litres of water to replenish relatively quickly by the end of that exercise. What that's going to do is it's going to make sure that my body is not only rehydrated to the point it wants to be, but I've got some extra fluid for other things that want to take place in my body during that time. So this is a bit of what I drew up on the board the other day. So ATP, PC, depletion of those things, and you want to rest. Lactic acid or anaerobic glycolysis system. Please don't use the lactic acid system as your terminology. You've got the hydrogen ions and inorganic phosphates. Don't forget, be careful with lactic acid. It's not the lactate, it's the hydrogen ions. You don't need to refuel anything food-wise here. You want to make sure that you're having an active recovery. We spoke about the definition of active recovery, doing the same action at a lower intensity. Massage is good to continue to promote blood flow, and the hydro or water-based therapies. Now, for those of you who are unsure of this, it's things like ice bath, okay, or even the hot-cold contrast showers, which I think are absolutely fantastic. This is just a personal opinion. I use them a lot. So basically what that means is that you're cycling through, turning the shower onto very cold, and then putting the shower onto nice warm temperatures. And I want you to think about this. We want to keep the blood flowing, so any lactate can be flushed to the liver, any hydrogen ions can get some oxygen that they need. So basically what this means is pretty quickly after exercise, you jump in the shower. And if you don't have access to an ice bath or anything, it doesn't matter. You warm the body up. When we warm the body up, blood's going to be flowing really nicely. Everything's going to be dilated. Those blood vessels are dilated, so lots of blood can flow through them. But we still want that muscle pump idea. So by chucking the shower on really cold, what it's going to do is it's going to tense us up. And when that tension takes place, that muscle pump is going to squeeze a lot of the blood out of those areas where it might be pooling. And then if we go back to that warm, it redilates those blood vessels and allows that blood to flow through. So usually we cycle through this about 3 times where we go cold, hot, cold, hot, cold, hot. And there's a lot of ideas out there about how long you spend in each. I like to do double in the warm and a single in the cold, which means if I go 30 seconds cold, then I'll go 1 minute in the hot. If I go 1 minute in the cold, then I'll go 2 minutes in the hot, and I'll go through about 3 cycles of this. And it is really proven to be beneficial to continue that muscle pump idea, and that's that hydrotherapy stuff, okay, the hot-cold contrast. Finally, aerobic energy systems, we deplete our fuels, whether it be glycogen or fats. We want to make sure that we refuel ourselves, so eating high GI foods, okay? We've got those different types of drinks. We've got the hypertonic, which we'll talk about at a later stage, but they have a lot of glycogen in there. There's your carbohydrate drinks like our Gatorade, and the hypotonic, which is a lot of our water, okay, which is replacing just that water and fluids. There's also the isotonic drinks, which we can talk about at another stage. You also want to make sure that you're doing the active recovery stuff here as well as rehydrating and refueling, so that if you have gone through lactic acid buildup at any point during your aerobic exercise, which a lot of athletes will, we can flush some of that out as well. I know that there's been a lot to take in this video, and for those of you that have stuck around to the end, I really do hope it's been beneficial for you. If we're in this lockdown longer than expected, we're not going to have these huge chunked videos for you, but I thought it was really important to just get this all over and done with very quickly. I want to have a couple of lessons coming up where they're very interactive about you completing some questions. We'll go on Zoom, we'll set some breakout rooms up. What I want to create for today is I'll put a Zoom link out to you for anybody who wants to seek clarification on anything, but I do want you to make sure that all that stuff that we need to be catching up on, peak questions, Enrolo questions, ensuring that our labs are written and up to date, those are things that are absolute priority right now, as well as understanding this fatigue and recovery. Essentially, that almost brings us to the end of our learning around this area of study, and we've still got a bit of time before our SAC in week 9. Mr. Smith and I have discussed trying to move on to some of our Unit 4 material even before the SAC takes place, which I think would be beneficial to you. But what we are going to do is we're going to be spending some time on some practice questions where I'll model some, we'll do some as a class, joint construction style, and then you'll do some by yourself as well. Enjoy.